projects. In this video, we are going to explain about the project, which is detection of mulberry ripeness stages using deep learning models. Let us discuss what is the project about. Mulberry ripeness detection is crucial for optimizing harvesting times, ensuring fruit quality, and maximizing yields in mulberry farming. Timely detection helps in preventing overripe or underripe fruit harvesting, which can impact the flavor, texture, and overall market value of mulberries. Conventional methods of ripeness detection in mulberries rely heavily on manual inspection, which is labor intensive, time consuming, and prone to subjectivity. Color and texture based visual assessments may vary among individuals, leading to inconsistencies and inaccuracies in determining the optimal harvest time. Moreover, traditional approaches lack scalability and may not be suitable for large scale farming operations. The project focus is to develop a robust deep learning based system for accurately detecting mulberry ripeness stages using image processing techniques. By leveraging advanced algorithms, we intend to automate and streamline the ripeness assessment process, thus enhancing efficiency and precision in mulberry farming practices. The proposed system integrates deep learning models trained on large datasets of mulberry images. By analyzing color, texture, and other visual features, the model can accurately classify mulberries into distinct ripeness stages. This automated approach minimizes human intervention, reduces errors, and provides real time feedback, allowing farmers to make informed decisions based on harvesting schedules. Coming to the objective, the primary objective of the project is to develop an automated system for accurately detecting mulberry ripeness stages using deep learning techniques, thereby optimizing harvesting times and improving fruit quality in mulberry farming. The aim is to employ Inception v3, AlexNet, ResNet 50, DenseNet, ResNet 18, and Exception, which are the deep learning algorithms employed in this project for ripeness detection in mulberries. The project aims to classify mulberries into 8 distinct ripeness classes, which is black overripe, black ripe, black semi-ripe, black unripe, white overripe, white ripe, white semi-ripe, and white unripe. The objective is to compare the performance of the deep learning models using evaluation metrics such as accuracy, precision, recall, and FN score to determine the most effective algorithm for mulberry ripeness detection. The goal is to benefit mulberry farmers, agricultural researchers, and stakeholders in the food industry by providing a reliable and efficient tool for optimizing harvesting practices, improving fruit quality, and maintaining market demands more effectively. To implement this project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement this project, we have designed various steps in the flow of work. So coming to the first step, which is importing the packages. In this step, necessary Python libraries and packages are imported into the project environment. We have imported TensorFlow for deep learning, NumPy and Pandas for data manipulation, Seaborn and Matplotlib for visualization, Flask for web application, and SQLite for database management. The next step is exploring the dataset. Here in this step, the dataset containing images of mulberries at different ripeness stages is loaded and explored. This step involves examining the structure of the dataset, checking for any missing or erroneous data, and gaining insights into the distribution of different ripeness classes. The next step is image processing using image data generator. Images in the dataset are pre-processed using techniques such as resizing, normalization, and data augmentation. The image data generator class from deep learning frameworks is commonly used for this purpose, which helps in preparing the images for training the deep learning model. The next step is data visualization. Data visualization techniques are employed to gain a better understanding of the dataset. This includes plotting, visualizing sample images from the different ripeness classes, and exploring the dataset. The next step is splitting the data into train and test. The dataset is split into two subsets, which is training set and a testing set. The training set is used to train the deep learning model, while the testing set is used to evaluate model's performance on unseen data. The next step is building the model. Here, a deep learning model architecture is designed and implemented. This step involves defining the layers, activation functions, and other parameters of the neural network architecture. The next step is training the model. Here in this step, the deep learning model is trained using the training data. During training, model learns to map input images to their respective ripeness classes by adjusting its parameters based on the observed data and the defined loss function. Coming to the next step, which is Flask framework with SQLite for sign up and sign in. Flask, a Python web framework, is integrated with SQLite, which is a lightweight relational database management system, to create a web application for user authentication. This allows users to sign up and sign into the application securely. The next step is user gives input of Mulberry images. Users interact with the web application interface to provide input in the form of Mulberry images for ripeness prediction. The next step is the given input is pre-processed for prediction. The input provided by the user is pre-processed to ensure compatibility with the trained deep learning model. This involves data normalization, resizing, or any other necessary transformations. Coming to the next step, which is training model used for prediction. The pre-processed input, which is images, are fed into the trained deep learning model, which predicts the ripeness stages of the mulberries depicted in the images based on learned patterns and features. The last step is final outcome is displayed through frontend. The predicted ripeness stages are communicated to the user through the frontend of the web application, providing a user-friendly interface for accessing the model's prediction and any additional relevant information. Algorithms which are used for detecting stages in the mulberry's ripeness are Inception V3. Inception V3 is a convolutional neural network and it is a powerful type of algorithm that analyzes images by breaking them down into smaller pieces and extracting features. These features are then used to classify objects within the image, similar to how the human brain recognizes objects in its environment. It is developed by Google. Inception V3 boasts impressive efficiency. Despite its complex structure with multiple layers, it requires relatively few computational resources compared to other CNNs. This efficiency makes it a versatile tool for various tasks in computer vision, often serving as a starting point for more specialized applications. Inception V3 is chosen for its deep architecture and inception modules, enabling it to effectively capture complex features and spatial hierarchies from Mulberry images, ultimately enhancing the accuracy of ripeness detection in the project. The next algorithm is AlexNet. AlexNet is a deep convolutional neural network architecture. It is renowned for its groundbreaking performance in the ImageNet large-scale visual recognition task. Significantly advancing the field of computer vision, AlexNet comprises multiple convolutional and pooling layers, followed by fully connected layers, and utilizes techniques such as Zillow activation function and dropout regularization. In the project, AlexNet is employed for mulberry ripeness detection due to its pioneering architecture and proving effectiveness in image classification tasks. Its deep layers enable the extraction of intricate features from mulberry images, while techniques like ReLU activation and dropout help prevent overfitting and enhance model generalization. Additionally, AlexNet's historical success in large-scale visual recognition challenge underscores its reliability and suitability for accurate ripeness detection in the project. The next algorithm is ResNet 50. ResNet 50 is an extended version of ResNet residual network architecture. It consists of 50 layers, including convolutional layers, pooling layers, and residual blocks with skip connections. ResNet 50 is known for its deeper architecture, which allows it to capture more intricate features and patterns from images, leading to improved performance in various computer vision tasks. In the project, ResNet 50 is selected for mulberry ripeness detection due to its deeper architecture and superior feature extraction capabilities. The additional layer in ResNet 50 compared to shallower variants enable it to capture more complex relationships and nuances present in mulberry images, enhancing the model's ability to distinguish between different ripeness stages accurately. The next algorithm is DenseNet. DenseNet is short for Densely Connected Convolutional Network. It is a deep learning architecture. Unlike traditional convolutional neural networks, where each layer feeds into the next layer, DenseNet connects each layer to every other layer in feed-forward fashion. This dense connectivity facilitates feature reuse and encourages gradient flow throughout the network, resulting in improved parameter efficiency and feature propagation. In the project, DenseNet is utilized for mulberry ripeness detection due to its unique dense connectivity pattern, which fosters feature reuse and facilitates more effective gradient propagation. By leveraging dense net architecture, the model can effectively capture intricate features from Mulberry images across different layers, enhancing the accuracy and robustness of ripeness detection additionally. The next algorithm is ResNet 18. ResNet 18 is a variant of residual network architecture introduced in 2015. ResNet 18 consists of a stack of convolutional layers with residual connections where the input to a layer is combined with its output using skip connections. These skip connections allow for the training of very deep networks without suffering from vanishing gradient problem. In the project, ResNet 18 is employed for Mulberry ripeness detection due to its well-established performance and efficiency. Its residual connections enable the training of deep networks which can capture more complex features from Mulberry images. Despite its relatively shallower depth compared to other variants like ResNet 50, ResNet 18 is chosen for its balance between model complexity and computational efficiency, making it suitable for deployment in resource constrained environments or scenarios where rapid inference is required. The next algorithm is exception. Exception is a convolutional neural network architecture. It is inspired by the inception architecture but introduces depth-wise separable convolutions which aim to capture spatial and channel-wise correlations separately. This architecture reduces the number of parameters and computational complexity while maintaining or even improving performance compared to traditional convolutional layers. Exception is selected for Mulberry ripeness detection due to its innovative architecture, which efficiently captures intricate features using depth-wise separable convolutions. This enhances the model accuracy in distinguishing between ripeness stages. Additionally, it is reduced computational complexity allows for deployment in resource-constrained environments, improving efficiency and enabling fast inference. We have used accuracy, precision, recall, and F1 score, which are the performance metrics to evaluate all the models built in the project. So here we have comparison graphs for all those metrics. This is accuracy comparison graph. Here in the accuracy comparison graph, x-axis represents all the algorithm names and y-axis represents accuracy score for each algorithm. Similarly, we will have for other algorithms also. First, we will know what is accuracy. Accuracy is a proportion of correct predictions in a classification task measuring the overall correctness of a model's predictions. This is precision score comparison graph. Precision is the ratio of true positive predictions to the total positive predictions, representing model's ability to correctly identify relevant instances while minimizing false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It is the ratio of true positives to the total actual positive, measuring a model's ability to capture all relevant instances without missing any. This is F1 score comparison graph. F1 score is the harmonic mean of precision and recall, offering a balanced measure that considers both false positives and false negatives, making it suitable for imbalanced data sets. The algorithm which performs well in all the metrics will be used for final prediction. As exception is performing well in all the metrics, it is used for predicting in the final prediction. To execute the project, first we have to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in HTML templates. This is the model folder in which we have algorithm information and that will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is a signup.db file. This file is a database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we have to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. And now we need to type the command python space app.py to compile app.py file. And now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the localhost, and the port, unless configured differently. So this is the localhost and this is the port. Now we have to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser, and this web page is built by using the Flask framework. To execute, first we need to register, so click on register. If you are new users, we need to fill all these details and click on sign up. I have already filled all these details and I have an account in it, so I'll directly sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password and now click on sign in. We have logged in successfully. So here we can see a choose file button. We need to click on that for uploading Mulberry images. So click on choose file. From the folder, I'm uploading the first image. Now click on open. Here we can see that image has been loaded. Now click on upload. Here we got the prediction that white unripe detected, which means that mulberry fruit is at white unripe stage. Now we will upload some more images. Click on home, choose file. This time I will upload this image. Click on open, click on upload. So here we got the prediction that white ripe is detected, which means that the fruit is at white ripe stage. We will upload some more. This time I will upload this image. Click on open, upload. So here we got the prediction that white ripe detected, which means that it is at white ripe stage. Click on home, we'll upload some more. Choose file. This time I'll be uploading this image. Click on upload. Here we got the prediction that black semi-ripe detected, which means that mulberry fruit is at black semi-ripe stage. So I'm going to upload one more image. Click on choose file. I'm going to upload the last image. Click on open and now click on upload. So here we got the prediction that black overripe detected, which means that mulberry fruit is at black overripe stage. Click on home. Click on choose file. We'll upload some more images. This time I'll upload this image. Click on open and now click on upload. So here we got the prediction that black ripe detected, which means that the mulberry fruit is at black ripe stage. Now click on log out. In this way, just by uploading mulberry images to the system, it will detect it is at which stage of ripeness. So the conclusion of the project is the project has been successfully developed, achieving its primary objective of automating mulberry ripeness detection using deep learning techniques. This accomplishment streamlines harvesting processes and improving fruit quality in mulberry farming. Among the deep learning algorithms evaluated, Exception emerged as a top performer, demonstrating superior accuracy in distinguishing between different mulberry ripeness stages. Its innovative architecture and efficiency in capturing intricate features contributed to its success. Exception, the most effective algorithm, has been deployed in the front end of the project. This decision ensures that users interacting with the system through the web interface benefit from the accuracy and efficiency of the exception in predicting mulberry ripeness stages. Looking ahead, the project holds promising opportunities for expansion and enhancement. Future endeavors may involve integrating additional features such as real-time monitoring, crop health assessment, and predictive analytics to further optimize mulberry farming practices. Additionally, collaboration with agricultural experts and stakeholders, which could facilitate the integration of domain-specific insights, ultimately leading to more tailored and impactful solutions for agricultural community.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.